Hello everyone. Today we are going to solve Bayes theorem problem number 4. So let's read the problem. A jar has 1,000 coins, of which 999 are fair and 1 is double-headed. Pick a coin at random and toss it 10 times. And now you see that each of those 10 times you see head. Then the question is, what is the probability that if you toss the coin again, you will see a head? And then the question asks, give your answer in 3 significant digits. So essentially asking us to be a little bit more precise. So I'll let you read this question, but I'll, as usual for every one of these problems, I'm going through the basics. So I'll go through Bayes theorem as well as Markov chain probability. So if you're already familiar with it, you can skip for the next 2 minutes, and then we will revisit this problem. So let's review some basics and then come back to this problem. So remember the Bayes theorem. So Bayes theorem essentially says that if you have probability of A given B, it can be expressed as probability of B given A times probability of A divided by probability of B. And we know the terms probability of A is the prior probability, and this one is the likelihood, and this one is a marginal probability, and this is often called posterior probability. So this is the Bayes theorem, and then the Markov chain rule is essentially if you want to compute probability of A intersection B, it can be expressed as probability of A given B times probability of B, or this is same thing as saying probability of B given A times probability of A. So this is the Markov chain probability rule, but in fact this can be extended to more than 2 variables. For example, if you want to compute probability of A, B, C, D, you can say probability of A given B, C, D times probability of B given C, D times probability of C given D times probability of D. Here I use the same order, but in fact it could be any order you can think of. Let's say probability of A, C, D times probability of A given C, D times probability of C given D times probability of D. So there are many combinations that you can actually write, express this joint probability as in a chain rule. So in fact you can derive Bayes theorem from this chain rule, right? So if you divide probability of B here, you get a Bayes theorem. So these are the 2 basics. Let's revisit the problem and then try to solve it. So the problem is essentially a jar has 1,000 coins, of which 999 are fair and 1 is double-headed, and we are trying to pick a coin at random and toss it 10 times. And then the question is, like, if you already seen 10 heads, what is the probability that the next one is also head, right? So let's try to express in terms of probabilities. Okay. So what is given to us? It's given that probability that a fair coin, this is a prior probability, is it's like 999 of them are fair, and the whole space is 1,000. And then it's also given that probability that it's a double is the remaining one, right? So there is one double-headed coin, so it's a probability of 10. But what is being asked here? Probability of the next coin, like 11th task is what is this probability? So this is the question that's being asked, but in fact you can express this as probability that you are going to see head in 11th coin, given that either the coin is fair coin after 10 heads, this is what you're going to determine, or the coin is a double-headed. So this is the whole space, and this one is something that you derived based on is observing 10 heads. So what you have seen so far is, like, there are 10 events, 1 2 3 4 5 6 7 8 9 10. So you have observed head, and so on, head. if you are asked after one toss, what is the probability that it is head here, it's like, in fact, what is the, you could express in the same way, but you would assume that it could be either a fair coin or a double headed coin, right? But if you observe 10 heads, and if you ask the question, was the coin that I picked is a fair coin or double headed, you'll probably give more probability than prior probability, right? It will be more than 1/1000, because you observed 10 heads. That should mean something, that maybe the coin that I picked is double headed. So after observing 10 events, if you're asking what is the probability of seeing a double headed, and that is what here we have. So this can be said, the probability of head given after 10 events, it's F10, it's a fair coin, right? Or it could be that it's a double headed coin. Probability of head given D10 times probability of D10. So our goal is to actually compute probability. What is the probability of D10 after observing 10 heads? What is that? What do you give the posterior probability for it being a double headed, and what is the posterior probability for being a fair coin? So that is our first task, which is to compute probability of D10, which is actually nothing but what is the probability of the coin is a double head given 10 heads, right? 10 heads. So this is nothing but probability of 10 heads times probability of it's a we are applying a Bayes theorem, times probability of D by probability of 10 heads. So if we expand this, let me do it here. So it's actually probability of 10 heads given it's a double headed coin times probability of double headed coin by probability of 10 heads given double headed coin times probability of double headed coin plus probability of 10 heads given not a double headed coin and probability of not a double headed coin. So this is the whole space, right? So that's how you compute this probability. So this one is actually, what's the probability that it's a 10 heads is if it's a double coin, you see all heads, so there is the probability is 1. But what is the probability that it's a double coin? This is where your prior kicks in, so it's actually 1/1000. And then here same thing, it's 1 times 1/1000 plus, and this event is probability that it's actually this part is a tail, and this is a fair coin, and this is also a fair coin. In this case it will be 1/2 times if it's a fair coin, it's 1/2 times head, right? So you're seeing first coin as head, second as head, third as head, and so on. So that's why it's 1/2. And then finally, what is the probability of not being a double-headed is actually from the prior, you pick this one, this is going to be 999 times by 1000. So this is, if you compute this one, this value is going to be 0.506. Remember, our goal is to calculate these values. So again, I'll write it here. Probability of H is what is being asked here, which is going to be probability of H given after 10 events, it's a fair coin, times probability of what is the probability that it's a fair coin after 10 tosses, plus probability of it being a double headed, and then probability of double headed. So this is the base, and then so let's compute all of those values. Simply we can say let's compute those values here. So we know probability of F10, right? So probability of D10 is what we already computed, which is 0.506. Probability of F10 is 1 minus of this one, right? And then probability of H head given D10. If it's a double-headed coin, it's always 1, what is the probability that it's a head given fair coin? This is going to be half. So we substitute these values in this equation, and you will get 0.506 yeah, this one, right? So times d10 is 0.50 times times this is 1 plus this term is going to be probability of head given it's 1/2 times this value 1 minus 0.506. So the total is going to be 0.753. Okay, so that's a value that we are going to be, we are asked about the third significant digit, and this is 0.753. So it's actually doing Bayesian theorem twice, so that's why it is a little bit complicated, but this is the process you need to use.